Hi everyone, my name is Daniel Ferreros Blanco. The title of this paper is Hierarchies of Reward Machines. This is a joint work with Mark Law, Anders Johnson, Krisha Broda and Alessandra Russo. Previous works have argued the need to endue reinforcement learning systems with the ability to learn at multiple scales simultaneously and learn with a rich structure of events and durations. We can do this using a recent work called reward machines. A reward machine is a finite state machine whose edges are labeled with propositional logic formulas over a set of propositional events that the agent can observe while interacting with the environment. A reward machine also outputs rewards for traversing its edges. The reward machine on the right is an example for a given task, which is observing a squid and a chicken in any order, followed by a table. And we get a reward of 1 when we transition to the accepting state and 0 otherwise. The accepting state is the state that is double circled. When exploited using hierarchical reinforcement learning, for example, through the use of temporally extended actions called options, the two previous needs are fulfilled. We can have a meta controller that selects which edge to take from a given machine state, and then we can select actions according to the chosen edge. However, there are two limitations related to the use of reward machines. First, the lack of modularity. So far, only flat reward machines have been considered. And second, that they are hard to learn using some of the current approaches for learning them from experience, unless they have just a few states. We address these limitations by allowing reward machines to call each other, thus constituting a hierarchy of reward machines, or HRM. Each call is accompanied by a logic formula representing a necessary condition to make the call. And we consider a special case of reward machine, A sub t, which is called the leaf reward machine, that returns control immediately and therefore emulates the edges that we have in the original type of reward machines. We show two properties. First, given an HRM, there exists an equivalent flat HRM, and the number of states and edges in an equivalent flat HRM may be exponential in the number of hierarchical levels of the HRM. We exploit HRMs using the options framework, akin to previous work on reward machines, and we distinguish between two kinds of options. First, formula options, which as the name suggests are associated with the formulas that appear in the hierarchy. In fact, they are associated with calls to the leaf machine. And then we have call options, which are associated with calls to other types of machines. The policies of these options are associated with Q functions for the formulas and the reward machines respectively. And the selection process works as follows. The policy induced by a reward machine Q function returns a call. And if this call is made to the leaf machine, then we select an action according to the Q function associated with the corresponding formula. Otherwise, we are going to select a new call if the chosen call was not made to the leaf machine. We also propose a method for simultaneously learning policies and hierarchies in an interleaved manner. The input that we get is a list of tasks, each associated with a hierarchy level. And what we are going to do is learn a hierarchy for each of these tasks. A curriculum method chooses a task instance pair at the beginning of an episode, and the agent interacts with this task instance pair for the rest of the episode, getting rewards from the corresponding task HRM. If at some point the trace collected by the agent is a counterexample, that is, the trace is not consistent with the task HRM, we are going to learn a new HRM. Okay, and we do this by feeding a set of counterexamples to an inductive logic programming system called ILASP that is going to produce a new task HRM that covers all these examples. We highlight that a trace is a sequence of sets of propositions that the agent observes while interacting with the environment. Experimentally, We show that policy learning can be faster in non-flat handcrafted HRMs, that learning non-flat HRMs is feasible in 2 different domains, and that learning a non-flat HRM is more scalable than learning a flat HRM, mainly thanks to the reduction in the number of states of the root reward machine in the hierarchy. I summarize the main contributions that we have made in this work. Firstly, HRMs, a formalism that composes reward machines in a hierarchy by allowing them to call each other. Second, a hierarchical reinforcement learning method that exploits the structure of an HRM. And third, a curriculum-based method for learning a collection of HRMs from traces. That's it. Thank you very much for listening, and I'm looking forward to see you in the poster.